So we'll continue with Python today. We finished off with loops and iterations. Just a short recap. Looping is done using the for statement. You can do loops with the range here with an index. You can have index from starting, end, and also with step. But what you also can do is you can loop over. You don't have to have an index to loop. You can iterate directly over the values in a list using the in statements for value, in values, and then it will iterate over the values in the list. And then you can also, of course, if you need an index, you can use range and then use len here to iterate over a certain length of a list, and then use the index notation here to get access to the elements. There are some nicer ways to do that as well. So you can do using the enumerate function. You can actually get an index and a value directly in the loop. And as also you can use the zip statement here to loop over multiple lists at the same time and get each item assigned to a variable here in the loop statement. So it looks something like this. And you can also have multiple loops, and you see you have indentations, multiple indentations here for the code blocks. And also you can loop over dictionaries using key value pairs using the items method of a dictionary. You can loop over the keys only using the keys function. And then also loop over only the values in the dictionary using .values. Then there is also a while statement where you can use to loop continues until a criteria is false. So in this case, the while statement here, and this is the condition to continue the loop. If that is true, it will continue looping. Then we continue with conditional statements. So if you want to test something, test the variable's value, you can use the if statement, and it works the same way as the loop. So you have a if like this, and then a colon. And every time you have a colon, you have a indented code block. So if I equals 0, print this out here. And if it's something else, that code block will not be executed. You can also have if statements where you have one block for when the condition is true and one block when the condition is false. So in this case you have if equals to 0, then we print out this. Otherwise or else we print out this part here. And if we put 0 here, you can see here that it prints out I equals to 0. And you can have multiple of these. So you can have start with an if, continue with else if or elif, a certain condition, another condition, and then a final condition here as well. You can also nested if statements. So in this case I have if I equals 0, I do this. Otherwise I have another if statement inside this here. So you can see that then this entire if statement belongs to the else code block here. It's also possible to, when you are looping, iterating over ranges, to control the loop itself. And there are two ways of doing that. That the break statement, so that breaks the loop and exits the loop and continues execution after the loop here. So this is the place where we continue the loop. We have continue that goes to the next iteration of the loop. So you're not interested to continue the execution of the block in the loop, just go to the next iteration value. So so this is we loops from 0 to 19, and if I equals 0, we exit the loop, or 10, we exit the loop, and if I equals to 5, we go to the next iteration. So we run this, it looks something like this. So you see here, I equals 5, then it prints out this one here, goes to the next iteration without printing out anything, and then when we come to 10, it breaks the loop, and we are out of the loop block here. So good to know. It's I think you should use them sparingly because it can be kind of hard to read if you have a lot of break and continues in the loop to kind of figure out where the code execution goes. So a bit sparingly use them. So just to kind of give you something to do. So if you're in the presentation now, there is a task here. You can see here. And your task is to kind of correct this code to see if you can find where the errors are. So I already filled in the code, so you can, when you feel comfortable, you can press play. And when you have corrected it, it should not print any error messages. Have you found errors? Oh, so okay. So what I will do is just run the code here, because you can get hints from the error messages. So you can see here, indentation error, unexpected indent. That means that the indentation in Python is really picky with indentation. So if you have a print statement here, the first statement in the block defines kind of where the code block starts. And I usually use 4 spaces. I don't use tabs when I do code blocks. So here's 4 spaces. Here is 1, 2, 3, 4, 5 spaces. And Python doesn't like when you mix. If you don't have a new code block, try changing the indentation. So the first error here is actually that we have an missing or the wrong indentation level. So if I move that back again, I run the code again. Oh, there is something wrong again. Now we have a syntax error. And the reason for that is that the for loop expects a code block. And there is no colon here, which is a syntax error. So we need to put the syntax error, put the colon here so that we can have an indented code block. And then we run again. Now you can see here another syntax error. So the parenthesis is not closed. That means that we are missing something here on the right side of the function call. So we just add a parenthesis there. And now it works. So Python is really picky with indentation, so you have to be really consistent with indentation in your code, especially within a code block, so that you don't vary outside and in, because it will complain. And also you need to always, for loops, for function definitions, for anything, you need a colon here, and that is, the next row will be in an indented code block. So I will copy our solution back again here, like that. So now it's wrong again. Okay. So another task that you can do here for a minute, so do a loop that loops over the list above here. So you can copy this in here, like that. And then in the next statement here, create a loop that prints out the values of the loop. Also try not using an index. Okay, so hopefully many of you suggested we should use a for loop. So one solution is to do for v in L colon for a new code block, and then remove that one here. We do print v, and that should do the loop here. You could also have done the other solution here for I in range len L, and then print vi as well. Oh. Sorry, L. Like that. But if you not require the index, I would rather go with for v in L colon print v, like that. Okay. So next part we will look at the building blocks of your code. So up until now we have kind of just learned the statements, how to create variables, how to loop and iterate, print. But if you get larger programs, you need to kind of create more maintainable blocks of code that you can reuse. And one way of doing that in Python and other languages is using functions or subroutines. And in Python, you can define your own function by using the def keyword. And the def keyword is then followed by the name of your function and a colon again, because functions are defined by the function definition and a code block. So in here you can see you have a print doc function, colon, and it's followed by a print statement here. So the print statement, it says to belong to the function now. So if you run this, nothing will happen, because the only thing you have done now is define the function. And nothing will be shown on the screen. It's just that Python now remembers that there is a function called printdoc. So if you call the function here, just like you did with the print statement, you can see here it calls the block and prints out the values, or the text. You can also add arguments or parameters to your function. You define it approximately the same way. So you have the function name, and then in the parentheses you put the variables you want to pass over to the function. So in this case I have a, and then I print the value here. I use a function here called str to ensure that it can actually print out anything you give that function. Because if you put in a float, it converts it to a string and prints that out. So here you can see here that now I have a function called print value. I define a variable called b with the value 42, and I pass this over to the function. So the actual, the a you define in the function is just a placeholder for any variable that goes into the function. So that's why we can pass b, c, d as a parameter here over to the function. So now you can see it took the value here, and then the function printed that value out by saying the value is 42. And also if you put a floating point value, because we have this string function here that converts any variable to a string, this will work as well. We can also have a Boolean variable, then it prints that out as well. So any value here can work. So what do you think happens in this function here? What if we define this function here? It's the same as before, but we assign the value a equals to 84. So the incoming variable we assign 84. What do you think that the b value will be here when we run this function? Anybody guess 84? Let's try. So the value is 42. And the reason for that is when you send a function value into a function, it's a reference to the memory location of that variable. And what happens here is actually that I define a new variable inside a function in Python, assign that to 84. But that is not the same thing, the variable coming in. So what you do here is actually create a new memory location where you store 84, and inside a function I reference that with an A. So it doesn't go out of the function. So all variables you define inside the functions are only available inside that function. So I can't access A from outside here. So if I try to print A here, it will complain because A is not defined. It's only available inside a function. So I pass B over here, and B will still be 42 when it comes out after I call the function. So how do we get out things from a function? So the easiest functions for doing that is the typical mathematical functions. You have a function that takes x as input and returns the computed value of some expression and returns that back. And to return things from a function, we use the return statement. Quite obvious. And here you can see I have a function here, f, and it returns sin of x. And then you can just call it here like this. So x equals to pi divided by 2, y equals to f of x. And that is just how it works. What you also can do, I told you a little bit about in start of the last lecture, you can return multiple values from a function. And what you do then is very simple. You just return, and then you return the variables with a comma separated. Then you have to catch them as well here in the call here. So in this case, x comma y equals to test 42. You have to have two variables to assign here. And also, if you're not interested in one of the values, there is a trick which I use, is that you just put an underscore as the variable return for those variables that you're not interested to take. Because an underscore is a valid variable, and if you have multiple, you can just x comma underscore 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 and so on. So if I run this here, you can see here that I got 2 back, and I get 1 here for the function call. You can also send lists over to a function, and lists can actually be modified inside a function. So you remember that the list is a data structure and it has its own references. So in this case here, if I have an external list A with 4 values, and I modify the first value here and assign it to 42, and here I call the list here and I print it out, and in this case you can actually modify the value. So scalar values can't be modified, scalar arguments can't be modified in Python unless there are lists. And you can modify a list inside a function by just like this. So I give you a short task again. So I want you to implement this mathematical function in Python. Just remember that you define functions using the def keyword. Okay, so the solution to this here is that you do def f, then you have to specify the parameters here. I have x, colon to define the code block, and if you want to return something, we need to use the return statement here. And here we can write the expression directly. So in this case, we can do 2 times, and if you're fancy now, you can do x double 2 like this, because 2 multiplications is an erased by. You can also do x times x like this, plus 2 times x plus 3. Then we can call this function here again, print f0, for example. And it gives you 3. So it's very easy to define new mathematical functions. And one nice thing with functions in Python is that they are actually, you can use them just like a variable. So you can actually pass a function to a subroutine. So you can create a function plotter, for example. And you just pass f as without a parenthesis, and then it's like an object you can pass along, and then you can call that function within another function. Next, we need to also organize ourselves. So when using notebooks, you're in kind of a different way of running Python. But if you're running Python outside notebooks, for example, which is to do code, you need to also organize your code not only in functions and subroutines, but also in modules. So modules is a collection of subroutines that have the same kind of organized in the same way. So you can have routines for printing stuff, utility functions, you can have finite element functions, you can have visualization functions. And each of those you group in separate modules. And you have probably also seen already that we have used import for several places. And import is a way of reading one of these modules and making these functions available to your code. And the really cool thing with modules in Python is that every Python file is a module by itself. So just saving a file with functions in it and a name will automatically define it as a module that you can import. So you don't have to learn too much. You just divide your code into multiple files and you have modules. So in this case here, the simple import statement here is import math. Math is the runtime library for mathematical functions. So if I do import math, the functions are available in the math module, and you have to prefix the function with math.syn, math.py, and that works. But it is a lot of things to type. So there is an alternative form. If you're not interested in the actual module name, but only the functions, you can use the from alternative import here. So from math, import star. That means that from the math module, import all the functions directly into my current context or current module I'm running. So then I don't have to put math in front of these anymore. So now that works directly. Using the star operator here when you import is sometimes takes a long time, because it will import everything, and that takes some time for the Python interpreter to do. If you're only interested in certain functions, you can specify them here as well. So you can specify sin and square root. So I just import those functions. That is quicker than using the star import. There are some you will see later on when we use NumPy that the preferred form of importing is actually using the import with the module, the import without the from. Because you have a lot of modules in Python that sometimes have the same function names. And if you import with from, they will clash. And you will overwrite the last one and you get a new function that you didn't expect. So for example, when we do use NumPy later on, we will import that with a short suffix instead. So that because the math functions here are built-in math function in Python, and in NumPy we will have our own math function that have the same name. So we need to kind of separate them. So as I said before, all source code files in Python can be modules. So for example, I define a module here. This black part here is the source code file. It has the Unicode things I talked about yesterday. It has its own math import statements. You define your function, and that is the module. So to simulate this usage of modules in a notebook here, I need to download my module file here. So it downloaded PrimePy, and if you look at the files here, you can see I have a PrimePy file in my notebook here. And so what I can do now is to use this file, I just import prime. And you never give the .py extension when you import modules, just the name of the module. So now you can see I imported this one. You can also see here that usually shouldn't print anything, but I think there is something in that file that shouldn't be there. Okay, so I imported the file, and now all the functions in that module is available to me. So I can check here, prime is prime true, and that is not a prime. So it's very easy to define your own modules, and it's also a good way to modularize your code. Especially if you are multiple people working on the code, you can have multiple modules, and each person is responsible for a certain module. So in many other languages, there is a kind of starting point of all programs where kind of the execution of your code starts. In Python, it's a bit different because any Python file can be executed. And Python will read a file from the beginning, start executing the statements, and running. But sometimes you want to differentiate between being a module and being a main program. So modules, when you import them, they actually execute the code as well, statement by statement. So if you have functions, the functions are defined and so on. But if you want to know if your code is actually imported as a module or run as a script, you can have there is a special variable that is set called name. And if you saw here before that when I imported prime, you said printed out prime here. And that is that print statement you see here, that's name here. So when you import a module, the name variable is the name of the module. If you instead run, let's see here. If you run the code from, for example, when you press play in Visual Studio Code, the module is run, it's not imported. And then that name will be different. So if I do import prime here, it says prime extra, that is the module name here. If I run it here, just like running in Visual Studio Code, you can see it says main. So if you execute a Python script, this name variable will be main. So usually when you have if you want to define a kind of starting point of your application and protect it from accidental import things, you usually do something like this. So I have import prime here, and I have if name equals to main, then I know that the code is being executed from the command line or by pressing play. And then I can execute my code. If I import this function, name will be prime main here, and nothing will happen. So you can see the differences. If I do run prime main, you can see here that it runs this code. If I import same Python, nothing happens. So you don't have to think too much about this, but you will see Python code with these statements in it, and then you know what it is. It's just kind of a way of checking if a source code is imported as a module or run as a script. So yesterday on the exercise we had a lot of questions on how to make your printouts nicer, and this is the next step we're going to talk about here. So how to format output data in a way that is more readable than just dumping out all the decimal places directly. So in Python, you do this using, and there are multiple ways of doing this. I will show you two different types. So as we said before, strings are objects, and objects have method that you can call. And there is a method on the string called format, where you can specify variables that will be filled into the string. So it looks something like this. So this string here, you can see it as a template, how you want the output to be printed. And each of these curly brackets will be replaced by a variable. So A will go into the first curly bracket, followed by a comma and a space, B, second, and third, and so on. And this way you can actually, you can set the templates. This is the way I want to print out my variables. So if I run this, you can see here it prints out with commas in between. But I can also have, if I want to have dashes here, and then you can see it formats the output according to your template. Okay, so now we have decided the kind of order of the things and also where the variables should go. It's also possible to reorder the variables. So by putting a number in it, it can put different variables in different places here. So 0 is the first variable A, 1, B goes to 1, C goes to D, and so I get them in the reverse order here. You can also specify like in Excel, you can put the numbers on the left side, on the right side, centered in the cell. We can do that as well. So you can add extra directives here inside these curly brackets. So the colon here says that we want to have 15, so the field should be 15 characters long. And you can see if you print this out here, by default, the string will appear on the left side and it will fill out until 15 characters. So that is the default. If you don't specify anything, you get 15 characters, and that is the field width. You can specify a greater than mark here. That will actually right align the text. So you can see here that it moves the text to the right side in the field. You can center it by using this, I don't know what to call, raise to operator or circumflex in French. Then we'll center the text in that 15 character field. You can also specify what it should fill out the spaces with. So before the operator here for centering, you can specify the character here. So now I have an underscore. You can see here it fills the characters here with underscores. You can also put a star here. Then you get stars. So that is the basic. So you can set the field width, and then if you combine them, you will be guaranteed that every value to print has the same field width. So you can easily create tables with the exact amount of spacing, so the values all align on top of each other. So formatting, you can also say that I want to have a floating or integer value. Let's put a D here. That means that it's expected to have an integer at that location. And then you can specify the same thing. You can specify the field width. You can have the centering, the field characters, and so on. So here you can see some output here of integers. And you can see here, sometimes it can be nice to prefix the integers with zeros, for example, when in a printout. And then you can do that with, I put a 0 here. Integers is kind of easy. Floating point is the more hard thing to format. And there are several different formatting options you have for floating point. So you have F for fixed format. Here you specify the field width, the first item here, .2, and .2 is the number of decimals. So in this case I have all these fields have the field width of 10, but with different decimal places here, 2, 4, and 6. So if you run this, you can see here that you can get 314, 3416, and 314593. And that is kind of, if you want to do tables of results, this is the way you kind of control the number of decimal places by using the fixed format. Problem with this format is when you overflow, then the field width increases. So you need to, sometimes it's not the best option to use fixed format in all. You need to know that it fits in your field size. You can of course solve that by using scientific notation. So that is E, and then every value will be in scientific notation. There is also an option of having it in the G format, I think. Then it will select the most suitable presentation format for your data. So G will either pick F or E depending on the situation. You can also do, instead of having 0, 1, 2, 3, you can actually use named placeholders in your template strings. So here I have X and Y, and that refers to the X and Y input variables here. So sometimes it's easier to read a template if you do that. So now you can see I plotted a coordinate here with a parenthesis first, and then the X value and Y value, and so on. There's also a way of using the format function here to actually refer to the actual variables in your code. So here I have params here, and I can see I have a dictionary here of value 1, 2, 3, and 4, and then I can put the dictionary into here using the double star operator here, and that will enable you to just put the values of the variables directly in the formatting string. And then I will also introduce you to something that kind of strange to, it's a bit, Every variable that you store in Python is stored in a dictionary in Python as well. So because of that, there is a variable called globals, or function globals, that returns a dictionary of all the defined variables in your current executable context. So you can see I have name, I have doc, and you can see here there's a lot of things coded in here. Everything as a dictionary. But what you can do with that is actually, you can use this in Python here. I have defined 3 variables. I put them in my formatting string, and I just give the format string globals, the dictionary globals, and then I can actually use the variable names in my code directly in my formatting string. And this was actually the precursor to the even cooler features in Python called f-strings. So f-strings in Python is a special string type that will read your variables from your code. So it basically does the thing here, this .format.globals, but it automates it so you don't have to think about it. So here I have the same code, 3 values, but I put an f in front of the string. Now I can put the variable names directly into the string. Using the same syntax we had done before with curly brackets, values here. I can also do the formatting here with what we show here. So fill with zeros, 10 with an integer. Like that. So this is, I think it's Python 3.6 or something that introduced f-strings. And it's a really nice way of putting numbers and controlling the formatting of numbers directly when you print a string. The only thing you have to remember is to put a small f in front of the string. So, let's see here, I have 5 minutes, this should work. One thing that we will use extensively in this project is the ability to read and write from files. And I mean, any programs that have used on Windows or Mac or whatever Office package opens files. It writes files. And we need to do that, be able to do that ourselves in our code. And to create a file or write to a file, we need to create a file object. And file objects are created by using the open statement. So if you want to write to a file or create a new file, we can do text file, which is a text object we want to create, open, and then we give it a file name, and then the second parameter here determines if we want to write or read. So W in a string is writing. So if you run this now, nothing will happen. The other thing that happened was that we told the operating system that we would like to open a file for writing, and I think it will be shown here. You can see here I have a myfile.txt here created. It's currently empty, so nothing. It's open and ready for writing. So to be able to write to this file, we have methods on the object to do this. And the main one is the .write method. So it's similar to print, but it doesn't give you a character return after each write statement. So write will continuously write to the file. So in this case here, I write filens innehåll, detta skrivs ut samma rad. And so \n here is required if you want to have a new line in the file. And then if you run this here. And then one thing we should note is that when you are done writing to a file, it's very important that we tell the operating system we are done with this file. Because operating systems today are really efficient in not writing directly to disk. So when you write to a file, it often goes to memory, and it's stored in memory until we don't use it, and the operating system writes it down to disk when it has time. So when we do close here, that actually tells the operating system we are done. And we can look at the file here. This cat here is a way of looking at the file inside here. So you can see here that this is the contents of the file. This part was written in the first statement. Next part in this statement here. Like this. This is the second write statement, and this is the third write statement. So write doesn't automatically go to the new line. So you have to have specify \n in the write statement to get the new line. So now we have a file, and now we want to read it back into Python. It's very similar. So you do the open again, but now we add a R parameter here, and that will tell Python that okay, we want to read a file, and now this file must exist on disk. So it expects that there is a file called myfile.txt, otherwise it will complain the file is not there. And what we can do, the easiest way is just use the read method, and the read method actually reads the entire file and puts it in a string. Not optimal for large files, so it's mostly used for small files. You can see here that it reads the file, we close the file, and then we print the contents. So contents now contains the contents of the file on disk. So to read in a more efficient way, we should read line by line. So if we have a text file, it contains lines of text, and then we read one line at a time. And what we can do here is we can open the file again. There is a method called readLine. It's just like it says. It reads one single line, stores it in a variable line. And then we continue here. While line is not empty, we just print out the lines. And the final thing we do in the while statement, we read a line. And if Python has come to the end of the file, the string will be empty. Close by, and then that's why we can check here while line is not equals to empty, continue looping. And if we run this, you can see here it writes this here and this here. And why do we have a space in between? So remember that print always adds a new line when we print. When we read a line, it reads the complete line, including the \n character. So when we get the string from readLine, it actually contains the character return, this character that goes to the next line. So when we print this line with the character return, it actually will first print the character return, go to the next line. The print statement will go one more. That's why we get this extra spacing here in between. If you want to remove that, we can do like this here instead. We do, every time we read, we do write strip. So we remove things on the right side and that is also the carriage return. And if you run it again, you can see there is no space between them, these rows. And finally, let's see how much I have. Yeah, we do this 2 here as well. So you can also loop with an iterator over the file, which is kind of cool as well. So you open a file, and you can do just like you do from a list for line in text file. And then it loops over each line until the file is empty, like this. And another option you can do is you can use read lines. That will read all the lines into a list, which is that you can parse afterwards. So then it gives you the option to read the file first and then loop over the line. You can see here that you get the list here with all the lines that are in the file. So let's take a 15-minute break, and then we continue with the final part here of file reading. Okay. So the final thing I will do before we go to the NumPy presentation is just cover that there's one way more to actually open files without thinking of closing them, and that's using the with statement. So the with statement is a special statement in Python that guarantees that the object being used in the with statement will be called the close method. So there are a lot of things in Python that have the close method to kind of finalize an operation or so on. So here you can see, instead of we doing open and assigning a variable, we do open, same syntax, as text file. So text file will be the file object. Then I do my operations here, and then I don't have to do anymore, because with the statements here in the block, before it exits the blocks, the close method of the text file will be called automatically. So this is just a way of guaranteeing that the files will always be closed after we have operator on them. So everything we do with the file we put in the with block here. And then you don't have to think about closing the file, it's done automatically for you. I will leave error handling to you to read for yourself on this presentation, so I will switch to the next presentation here, which is Introduction to NumPy. So, yesterday we talked about some of the data types in Python, specifically lists, and you can have nested lists. And it's tempting to start to do matrix library, matrix computation using lists, but they're extremely inefficient for computational tasks. So during the many years now, Python has had an external library called NumPy that is specialized in computing on arrays or blocks of data. So it's an extension. An extension is similar to a module, but it's actually compiled code. So it actually is compiled in C using extremely optimized math libraries in the system. So how do we use NumPy? So NumPy is imported for use using the following convention. So I told you before that sometimes it's better to use import statements to import modules. And there's actually another form of import that we will also use for CalFem. It's import as. So if you want to reduce the typing we require to use the NumPy library, we can import NumPy as NP. So instead of putting NumPy before every function, we just put NP dot. And this is actually a convention that people have been using on the web to actually use NumPy, is that you import it using that. So you get an NP here. So let's run that. So now we have all the functions available for us. The main data type in Python in NumPy is the array object. And array is the kind of container for our array, for a single array. And you can create arrays using the np.array command. And it has two arguments. First is the data to be initialized to the array. So in this case here I have a list here as input with 4 integers. And then the second argument here is the data type that you want. So NumPy is really picky, but you need to actually just, it has a data type for all the values, have a single data type. So in a list you can have different data types, but that is not the case in NumPy. So a NumPy array always has the same data type. If you don't specify the second argument here, it will determine the data type from the initializer list here. So in this case, if I didn't specify float, it would be an integer array. So you can see exactly what happens here. You can see here, now we have an integer array here, because the values here in the initializer list here is actually integers. And the same thing, if we put floating points in the list, you get a floating point array. You can also have multi-dimensional arrays. So what we showed before is a one-dimensional array. Now you can have, if you put a nested list here, you will get a two-dimensional array. So it's very similar to defining matrices in MATLAB. So you see here, also if you print them, it will print them in the right dimension. So if it's 2 by 2, you get 2 rows in the print statement, and now we have 2 rows here in the second argument here. Something that you need to kind of also look at, what is an array actually? And when you allocate an array, memory will be allocated for all the values in that array. But they are not stored in a two-dimensional array is not stored as a two-dimensional array in memory of a computer. So the computer can only understand linear memory. So when you allocate a block of memory in the computer, you will get a long array of memory cells. And what we do with arrays is that we interpret that long thing in memory as a two-dimensional, three-dimensional, four-dimensional data structure. So if you look here, we have a shape here, or array, which stores a lot of values. And in memory, it's stored row-wise. So they are stored 1, 3, 7, 9, 0. So you can see here, this is how the array is actually stored in memory. The two-dimensional things are just a construct to get to different parts of this long array. So a computer never stores, the concept of two-dimensional arrays is just something that we have defined in so it makes it easier for us to work with data. You can figure out the shape of an array using some of the attributes of an array object. So there is, for example, this shape attribute that gives you the number of dimensions of the array. So here I have 4. So the first one is a one-dimensional array. So you have 4 comma. That means that it's one-dimensional array of 4 elements. Second one is a 2 by 2. And the third one here is a 2 by 2 by 4 array. So shape can be queried the number of rows and columns in the different dimensions. You can also, one easy way of using it is if you want to assign variables that contains the number of rows and columns in an array, you can use r, c equals to b.shape. Because shape is a tuple, it can be assigned to 2 variables like this. And then it's an easy way to get variables that contains the number of rows and columns of a certain array. You can also query the number of dimensions of an array using the ndim attribute. And you can see I have 2-dimensional for the B array. And there are several other ones as well. So you can actually query the data type of the array. So that is something that we don't usually do in Python, but as this is very important for computations, it's actually stored as an attribute here. So dtype here is the data type. The dot size is the number of elements in the array, the total number of elements. And item size is the number of bytes of each element. So a typical floating point value is stored in 8 bytes. It's a double precision floating point. There is also a 4-byte floating point, which is a single precision floating point. When you do finite element, usually you want to have double precision as 8-byte floating point. So let's see what we have here. So now this is an integer. You can see here that it's 2 by 2. It's 2 dimensions. It has a 64-bit integer. It has the size 4. The total number of elements is 4. And every element size item in the array is 8 bytes. So if I add, for example, float here, you can see I have a float 64. And 64, that is 8 by 8 bytes. So that's this is the number of bits. So it's actually 8 bytes. We can change the shape of an array as well. And this is just a function. You don't have to remember this function. It's just a function that returns the array's memory location in memory. So I will show you what we're going to use that for. So the reshape method can be used to change the dimension of an array without actually changing the number of elements in the array. So as I said before, the array is stored as a one-dimensional construct in memory, but we can interpret that by specifying how many dimensions, the different dimensions we have in the array. So if we look at here, I do print A, so I print out the array, and then we do memory of A, so that we'll get a memory location of this array in memory. Then I do reshape here to do it from a 2x2 to a 4x1. So it's still 4 elements. And then I look at the flat array that I get back here, and the location of the memory for that as well. So what you can see here now that I created A as an array. The memory location is 16, 16 at the end. I do a reshape of that, return that to a variable A flat. And you can see that A flat is the same array. They point to the same memory location in memory. And you will see that a lot in NumPy, that it tries to avoid copying at all costs. Because if you are working with really large arrays, that will be the largest part of your computations, is moving and copying data in memory. So NumPy goes to great lengths to avoid doing any copy. So this reshape operation is just a way of reinterpreting an array with different rows of columns, but the same number of elements. That's why we also get the same memory locations here. So you have to be aware of that. If you do the reshape, you still work with the same data in memory. So if you change A, it will change A flat. If you change A flat, it will change A. Yeah, that's exactly what I said. So here I change the value 0, 0 in 42 in this A array. And here you can also see a difference here. Rows and columns starts with 0, not 1. That's different from MATLAB. And you can see here 42 is shown in A, but also in A flat. If you don't want that, you can use what we did yesterday, the copy operation. So if we do C equals to A.copy and change C, it shouldn't affect A. And it didn't. So C is 84 here, but it's 42 there. A is still 42. And you can also see that the memory locations are different here, which is also an indication that now we have a copy. C points to another memory location. Yeah, then I have some other examples here as well, just how you can reshape in different ways. And also, reshape is not the same thing as transpose. So the transpose function is the linear algebra transpose operation, which is not the same as reshaping it the same form. So just remember that. Don't use reshape to transpose matrices. If you want to change the size of an array, you can use the resize operation. And that will actually change the number of elements in the array. So here I have a 2x2, and I change it to 9x9. And this command will also reuse the values inside the original array when it expands it. So here you can see 9x9. It uses the values in the original array when it resizes it. So you can see it resizes in different ways here, but it still kind of keeps the values that from the original array. This is a costly operation again, because it will reallocate new memory and new arrays. Reshape is not, it doesn't cost you anything. It's just a reinterpretation of the array. Okay, so creating arrays using mp.array is a bit inefficient if you want to create large arrays. So to be able to create large arrays, there are some functions for doing this. And there you will see some relationship with MATLAB here as well. So if you want to create arrays that are filled with zeros, you can use the np.zeros command. Then you give it the size of the array you want to create. And you can see here it will create a floating point array of 5 by 5 filled with zeros. By default, it uses floating point. If you want to use another data type, you use the same kind of syntax as in the array. You just specify the data type here, int for integer, and it will create a 4 by 4 with zeros as the 0 integers in it. And of course, if you want arrays just filled with ones, you can use the ones command. Works just like the zeros command, but it fills with ones instead. You can also define, just like we had the range command in the for loop, we can define an array range. And it works the same thing. It creates a range of values and stores those in an array. So in this case here, I will create an array range starting from 0 going up to 9. And that will be an array in itself. So this is not a list, but an array with integer values in it. And this is you can do some tricks with this. So if you create a range of 100 values, you can reshape that 10 by 10, and then you get an array that counts from 0 to 99, like this. And that is this operation here is not costly, because the costly operation is done in a range, which allocates the memory for the range. Reshape just creates another variable that interprets that range as a 10 by 10 array. You can of course also give start and end values here and the step length, just like we did with the normal range command. You can give the data type here as a floating point at the end. So that is a way of creating ranges and arrays. You can also create the identity matrix using the identity command. Should be also similar to MATLAB. Then you see you have on the diagonal you have ones here. If you want to plot things with plotting libraries later on, the A range is sorry.
Just a quick question. If på svenska.
Yeah.
Att när man har från minus 10 till 10, om man då har kommatecken att man har från minus 10,5 till 10,5.
Ja.
Hur stora steg kommer den gå emellan då? Kan man göra det?
Ja, you can have a floating point step length. Yeah. So but actually what I want to say, if you want to do stuff like that, you should use the linspace here command, which I'm showing now, because it's more guarantees you to get the start and end values in the list. So the linspace here, you give a start and end point, and then you tell it how many values do I want to have in that range. So it creates an interpolation between those values and returns that as a X range here. So you can see 0 to 1. If you do that with the A range, it's not guaranteed that you get the last one. So here you will get, one will always be included because you have specified it in that. So you can, and that is very useful if you want to do plot, for example, a function. You can create X as a linspace, and then you create Y as a np.sinx, for example. I think you have to do the exercise yourself here, because I'm a bit short of time here. So, yes, array expressions. The nice thing with NumPy is that it actually contains a lot of the functions that are part of the math library. So what you can do is all arrays, if you use normal operators and scalars, it actually will compute, use the arrays, and if you add, for example, scalar, it will add that to all of the values in the array. So let's see here, we create a 5 by 5 array here with some numbers in it. If we do a plus 3, the value 3 will be added to each of the values in the array. You can do element-wise multiplication by using a multiplied by 3. So this is not this is a array scalar operation. So you can see here that it multiplies the array with 3. But the most cool thing is that you can use functions on the array. But you need to use the prefix function here. You can't use the normal math functions in Python because those don't support arrays. So if you want to use sin on an array, you need to use the NumPy version, so np.sin a. And you can see it calculates sin on every value in the array. You can negate the array, and you can add two arrays together. You can also do so if you have different shapes of arrays and you add them together, the values will be repeated. So it's not completely linear algebra here, but it will do stuff like that. So what if you don't want to do matrix multiplication? So as I said before, the multiplication operator is for element-wise multiplication. If you want to do linear algebra multiplication, you can use the dot operator. So a dot a, that is will be a matrix multiplication. But you can also use the at operator, and at is matrix multiplication. So if you want to multiply two matrices together, you do a at a, and those will it will be a matrix multiplication. So the arrays in itself does not interpret themselves as matrices in a mathematical form. They are arrays of values, and they have some functions for creating arrays that can be used in linear algebra, but itself they are kind of generic data structures. One other thing that is important is to be able to kind of extract values from an array, of course. So very similar to lists. So you use the square brackets to access values. If you have a one-dimensional array, you just like a square bracket, and you get the third value here. So 0, 1, 2, that is number 2. It checks out. And you can also access in a two-dimensional array, you just do square brackets and then the rows and column to get the access to the certain elements. Assigning values, same thing. You go the other way around. You give the location and the value. And if it's two-dimensional, you have row and column, and then assign the value. Works the same way. Just with list, you can use sophisticated indexing index notation to get access to slices of the arrays in different dimensions. So here I have a one-dimensional array. I can access a 4-element array using 1:5. So it uses the same syntax as for ranges. Starts at 1, goes up, but not including 5. And then you get 1, 2, 3, 4, 5. 5, oh, sorry, 4. Sorry. Then I also would go through a bit with when you do all these things here, the slices. NumPy tries to avoid doing any copying if it's possible again. So if you do a slice, we can check here. So I have a 25-element array here, and I do b equals to a 1, 2, 5. And there is a data here that shows you the actual location of the array in memory. The memory of is actually the starting point of that array. And you can see here that a and b are different on the start and the memory of, but they belong to the same memory block. So by doing slices, it's actually a view into another array. And if you modify that, it will actually modify both of them, just like we saw before. You can see here b0 equals to 42. You can see it because b starts at 1. 42 is assigned to the 1 position of the global array. So you can see it goes to great lengths to avoid copying. But you also need to know that if you change things, it will change in multiple places. And then there are some other things here. You can use the same ideas with lists that you can go backwards. So with -1, it's for example, here I get the last element of the array. If it's two-dimensional array, I can get the last row. And then if you have two-dimensional here, you can see I can get all the rows in column 0. I can all rows in column 0 and 1. And a lot of different indexing methods here that is very useful. And you can also, there's no need to assign an array, for example, a row in an array with another array. So if you, for example, here, I want to assign row 1 of a B array, I can use a list. So I can just take a list and assign that, and that will be automatically transferred over. So here you can see here I assigned here 42 here in that row here. And let's see, I didn't run that one. And this is assigned this row here. So it's very intuitive in that sense. If it should work, it probably does. Sometimes if it is long lists, it could be more advantageous to convert a list to an array before assigning it. But if it's small values like this, use lists. There are also methods that you can call on the arrays. So I create an array here. For example, sum. That will sum all the elements of the array to a single number. You can sum the columns only if you want to, or the rows by specifying argument 0 or 1 to the sum function. And it sums either in columns or in rows. And you can do the same thing with product. So if we can do product in the different rows here, and you can calculate the product of the different columns. Finally, I want to show you there is also a matrix object in NumPy. They want to deprecate this, so I would say recommend using arrays instead of this, but it's just show you that it's available. The difference is that the matrix object knows how to do linear algebra. So if you want to have more compact notation for matrix expressions, you can do that with a matrix object instead. So here you can see that you have you can give a.t, that is the matrix transpose of A. The multiplication operator is interpreted as matrix multiply, and a.i is the matrix inverse. And then also, because arrays can be really large and it can be cumbersome to read and write data to and from arrays, NumPy is actually built in support for reading and writing arrays. And it's similar to MATLAB, where you can save .mat files of arrays. And here you save NPY or NPC files instead. But it's the same thing. And they are text files. But you can also write them to binary files. So how does that work? So in this case here we have created one X array with a linspace, 100 items. I just do random numbers for X for Y. And then I can do mp.save and then save it as a file here, and I will give it a file name and the variable I want to save. So now it will create two files, one xp and npy. Let's see if we can preview that one. Okay, we do. If we do also do .cat, you can see here that they are stored as binary files. That's why you get the kind of garbage out here. So they are stored in a very efficient format. Reading them back is very easy. You do load instead of save. and you can see here that we can get the numbers back again. So this is a way of, if you want to save the computation you're doing, you can save it down to files, and then you can read them back again to the new array again. So this is something I will go for the next lecture, the matplotlib library. So I imported here as plot. It has the same plotting commands as MATLAB, and so here you can do X, Y, and then a marker here to show what should be shown on each of the dots. You can also, if you want to combine multiple arrays into a single file, we can use the open statement we did before. And the only difference is we need to do WB because we want to write to binary files. So that's the only difference. And then instead of specifying a file name, we can specify the file object here as the first parameter. Then it will save both of the arrays in a single file. So we can combine them, and then we have to do the same thing in the other way around. We do load X and Y again, read binary here as well. And now we should get the same points back again from the file. The final thing I want to talk about you today is also how to solve equation systems. To do that, NumPy has a special function for that, but it's not directly available mp.solve. It is available in the submodule called leanalg. And then there is a solve here. And then you give an array and the solution vector here. The right-hand side. And then it will calculate the X solution. Like that. When we are going to do finite element, we will use a special version of solve that is part of the Colfam toolkit because it can handle boundary conditions. This doesn't handle boundary conditions, so that's why we need to have a different one in the thing. But it's good to know that there is a generic equation solver built into NumPy as well. So that was what I wanted to talk to you about today. I'll stop.